Hey there, this is Franco, and the purpose of this video is to talk about building a small CNC controller that would be suitable for something like a mini lathe, or maybe, well, most definitely, a small benchtop milling machine like the Harbor Freight mini mill or something about that size. So going to try to give you a bunch of information here, but I'm not going to try to overwhelm you with too much boring and useless details. When I'm all said and done, there is going to be a wiring diagram that I will dump in a Dropbox, and I will put a hyperlink in the description of this video so you can follow it and get the wiring diagram as well as any other information that I think is useful. So here we go. So this is a nice little controller, and it's working really well. Just a quick little demo. I can rapid the carriage at 70 inches a minute. It's really nice. The x-axis is moving pretty well too. Probably capable of running it faster, but not going to talk about that because that's not the point of this video. But really nice controller. We have spindle feedback. You can see so that's working, and that is accomplished through the spindle index sensor that I make. This is one of my prototype-ish looking ones. I have some cleaner ones now that I make with my 3D printer, and soldering's a little nicer, but you get the idea. So something that I make to go along with the mini lathe conversion kits. Most important thing right here, e-stop. That works for sure. Gotta have that. And lost my mouse. And the limit switches work too. So probably should have got that a little closer before I started it. There you go. So for me, that's kind of like the definition of the basic CNC control system. You have the movement, you have the limit homing switches, the spindle feedback, e-stop, of course, and you know, you can go a lot further with it, but to me, there's the basics. So before I talk a whole lot more about that, let me just jump over here. So we'll get rid of this. I have a couple of things I wanted to share. So this kit's based off of the Long's Motor DM542A driver. It's using the 23 HS9430B stepper motors. It also comes from Long's Motor. It's using the DB251205 breakout board and the 350 watt 36 volt power supplies. All that stuff comes from Long's Motors. So before you get into building your CNC controller, it's probably good to just know some of the basic stuff. So where do you begin? How do you get started? You could do a whole bunch of calculations and formulas and figure out, you know, how fast you want to move. You know, you can figure out the mass of your machine and how fast you want to move it and what the acceleration should be and all that stuff. But most guys working in their garage or their basement, you're probably not going to do that. What you're probably going to do is jump on eBay and look for maybe one of the package deals that's available, and you'll find that this DM542A and this 23 HS9430B motor, this is a real popular deal. It's priced really good, and it's definitely big enough to run a small lathe, small mill, small router, those types of machines. So where do you get started with all this? Well, you maybe start with the motor, right? So there's a whole bunch of things to say about the motors, but there's a lot of questions like, if I use this motor, what type of power supply, what should I do? So I thought I would give you some information first. So this is a really nice document from Gecko Drive. I'm sure they make really, really nice stuff. I don't use their stuff. It's expensive, and from what I can see, it's not, rather than setting things with dip switches, you have to solder resistors in line with your motors and stuff like that. So I don't want to mess with that. But they have really good documentation, so I'm sure their stuff probably works really well too. So when it comes to calculating the power supply, they give you this nice formula. 32 times the square root of the inductance will give you the max voltage. So I just happen to have the drawing here for this motor, and the inductance is 6.8 millihenries, which is the unit that they give you the formula in. So what the formula will tell you, if you do the math, that the maximum voltage for this motor is 83.4 volts. So that's the maximum it can handle. It doesn't mean that that's the ideal voltage. So generally, more voltage translates into higher rapids, higher feed rates or whatever, but it also means more heat. So you could sort of think of it, 83.4 volts is the max. My vehicle redlines, the motor redlines at 6,000 RPM, but it doesn't mean that I want to run around all day long running that motor at 6,000 RPM, right? That would be kind of ludicrous. And that's kind of what you can think of this max voltage as. The motor could handle that, but it doesn't mean that that's necessarily the best place for you to run your motor all the time. So if you don't know the inductance of your motor, they give you this other nice little formula or rule of thumb that you take the motor voltage and multiply it between 4 and 20. So the voltage of this motor is 4.8 volts. And if you do the math according to that rule of thumb, that means you should be between 19.2 and 96 volts. So I guess as a rule of thumb, that's good. So there you go. So that's what we got. These are 36 volt power supplies, and that's what I'm going to use. And I think they'll do rather nicely. The next thing probably ought to talk about, because the power supplies are pretty straightforward. I mean, this power supply is capable of outputting 10 amps, 36 volts at 10 amps. So if each of your motors is, if you're going to run each motor at 3 amps or whatever you're going to set your driver to, right? So you basically got to make sure you have enough amperage to cover all your motors. For these switching type power supplies, it's good to have, you don't want to cut it too close. You want to have a little bit of extra headroom there when you're getting your amperage or speccing out your power supply with amperage. So this thing can output 10 amps. Let's just say, worst case scenario, you're running 3 motors and you're running each of them at 3 amps. So you have 1 amp to spare. It should be adequate. And the reason why I say that is the Long's motor people kit these things together. They sell them all the time, 1 power supply with 3 drivers and 3 motors. So I'm assuming they wouldn't do that unless they felt pretty confident that it was a good match. So there you go, switching power supply. I guess there isn't too much else to say about that. Next thing probably ought to talk about is the driver. So I really like these drivers. They're neat and clean looking. They have really nice screw down terminals. You set everything with dip switches. They have a nice big heat sink on them. I think they're really good. They have this feature, half current mode. So when the motor is at a standstill, it cuts the current in half. That's really important. I wouldn't buy a driver without that. And they have lots of nice settings. You can change all these currents with dip switches. So this motor, 0.71 RMS all the way up to 3 amps RMS. So this is the next thing I'm going to talk about. So when you look at your motor, The motor says it's a 3 amp motor. When you look at the driver, you have two columns. You have peak amperage and root mean square amperage. So how do you translate this into that? So I'm not an electrical engineer, for sure. That's a fact. But I did a little research, and first you have to understand the difference between peak and RMS. So the rating on the motor, from what I can tell from everything I've read, this is 3 amps, like peak, steady, consistent current, like a straight line. But your stepper motors, especially when you get into microstepping, they output the frequency in a sine wave, basically. What do they call it? Sinusoidal waveform or whatever. So peak voltage, you can see, is like the blue arrow. That's the peak or amperage or whatever, peak current. Peak current at the top of the curve. RMS, you can see that red line is a little bit lower than the peak. Well, basically what it's doing is it's averaging out that waveform into what it would be if it were like a straight continuous current. So that's why you see the peak is always going to be greater than the RMS, and there's a direct relationship there. If you do the math, you'll see every one, the relationship is the same. I forget what the number is. You can look it up online. So anyway, motors are spec'd out, from what I can tell, that 3 amps is 3 amps RMS. So where would you want to set your driver? Well, you might be tempted to max it out where it says 4.2 amps max, 3 amps RMS. I haven't tried that, but I suppose there might be some situations where that would be appropriate. So here again, just like the voltage, this is the max rating, the max thing that it's capable of handling. It doesn't mean that you need to run it there to get ideal performance. In fact, the enemy of stepper motors is heat. So if the motors get too hot, they lose steps and they start to do funny things. The rule of thumb that I've been told to use is kind of like if you can touch the motor and keep your hands on it, it's probably okay. If it's getting so hot that you can't keep your hand on it, you're probably cooking it. So here again, I'm going to be a little bit more conservative. I am going to, if I remember correctly, I think I set all my drivers there at the second to highest setting. So I'm going to run at 2.69 amps RMS, 3.76 peak, and you may even want to drop back to 2.36, 3.32 peak. And like I said, just sort of monitor the heat on the motor. Something else about these. So I don't know if you guys are familiar with the little story about expensive smoke. All electronics are secretly powered by very expensive smoke that's trapped inside of them, and if you do something to release the smoke, the electronics will no longer work. Well, it's true. So I mistakenly read I had the wrong manual. I had the manual for a different driver, and I'm not going to tell you what I did because I don't want you to be confused. Well, I guess I'll tell you what I did. I had the driver for the manual for a different driver, and that driver had an auto setting function, and then it involved flipping one of these dip switches while the thing was under power connected to the motor. So I lined up all 3 of my drivers, hooked everything up, and flipped all the dip switches. And unbeknownst to me, I fried all 3 of them. And the bad thing was, it wasn't like a total catastrophic failure. It made them fail in like a very intermittent way, which took me several hours to diagnose because one would move, one wouldn't move. One would only move in one direction, it wouldn't reverse. It was crazy. very frustrating. So whatever you do, do not flip these dip switches while the thing is under power. Just do not do it. Now, fortunately, because I have several of these that I smoked, I can take a picture of the inside of one and not really worry about it, because this thing is now a very expensive paperweight. So that's what the inside of these drivers look like, and pretty neat and clean, nice stuff. It doesn't look like junk. You can see everything down there on the bottom, fastened to the heatsink. So, in general, I would say these things are pretty nice. I have some cheaper TB6560 boards. You can buy them for like $5. I don't think I'm gonna ever use those because they just look like garbage. So, okay. So now we talked about peak RMS, we talked about voltage. Next thing you're probably gonna have to do is talk about your pulses per rev. So, typically 1.8 degrees per step. So full step mode translates into 200 steps per revolution. These drivers, they don't even let you, there's not even a setting for that. The lowest setting they have is half stepping mode. And I think that's not really a bad thing, because honestly, in my opinion, rarely ever do you get to run your stepper motors in full step mode on a CNC machine, because the motion is pretty choppy. So depending on your setup, your lead screws, your gear reduction or pulleys or belts or whatever, you're going to need different pulses per rev. But I try to get it to where the smallest increment on my machine is like 1 or 2 tenths of an inch. Very rarely do I need more resolution than that for the things that I make, and that seems to give me a really nice smooth feed rate. If your resolution is like half a thou or 5 tenths, it'll start to look choppy. If the resolution is 1 thou, it's definitely going to give you a really choppy feed rate. But for what I do, what I've seen, if I get the resolution down to 1 tenth or a couple of tenths, it seems to work really well. But here's the so you might be asking, well, why not just dial this thing all the way down to the finest resolution you can get? Make it as smooth as possible. Well, here's why. So here's another really nice document. Found this off the internet. Basically, this is the torque curve as you increase microsteps. So at full steps, or 200 steps per rev, you're going to have 100% of whatever the torque is, the holding torque. At half stepping mode, you're down to 70%. Quarter steps, you're down to 38%, and so on and so forth. So you can see how that drops off pretty quickly. So you don't want to increase microstepping any more than you absolutely have to. The more microstepping you do, the less torque you're going to have out of your motors. And you'll notice when you're playing with your stuff here that when the motors are going slow, you won't really see it. But as soon as you start to accelerate or try to jump up to a faster feed rate, you'll see them stall. So keep that in mind when you're picking your microstepping. Other than that, general things to know. This is the breakout board that I used. In addition to the power supply that runs your motors, you're going to need a separate 5-volt power supply for this thing. I have another video about this breakout board, so I won't spend too much time talking about it. If you want to know more about that breakout board, check out the other video. You're probably going to have to do some soldering. I have both a 30-watt and a 60-watt soldering iron. I really like I use the 30-watt whenever possible, but every once in a while I get something really big that I need to solder, and the 60-watt soldering iron works a lot better. If you've ever tried to solder and been frustrated, I'll bet you it's because the tip of your soldering iron, like the solder wouldn't stick to it, and if you can't get that to work, then it's not going to stick to the wires. If you've ever had trouble soldering, or if you've never had trouble soldering, either way, I highly recommend you go and get a container of this at Radio Shack. Tip tinner and cleaner, and this stuff's awesome. It's kind of looks like a chalky, hard candy kind of texture, but when you put the hot tip of the soldering iron in it, it cleans the tip, it tins it, and it really makes soldering a whole lot easier. As far as solder goes, just generic old like 60-40 solder works great. It has to be rosin core. Without the rosin or the flux in the middle, nothing will work. So you have to have this. It has to be solder for electronics. As far as wire, for the 110 volt stuff that I connect, I use this 14 gauge stranded appliance wire. It's flexible, has a really good heavy duty jacket on it. You can buy that at Home Depot. For the 5 volt connections, I use hookup wire. I buy a 22 gauge hookup wire. I buy that from Radio Shack. For like the motor leads, the things that I use to connect the motors and everything, I use 22 gauge stranded security system wire, which is also available at Home Depot. So you can get, for these NEMA 23 motors, the 22 gauge 4 conductor is a good motor or a good cable to use for the motors. They also make a 2 conductor that I use for things like e-stops. So that seems to be your choice. You either get 2 conductor or 4 conductor. It's stranded. It's has a shield on it. It's good wire. Available at pretty much every Home Depot I've ever seen. These connectors, these are called aircraft connectors or GX12 connectors. So these are GX12, GX12-3, GX12-2, GX12-4. However many connectors you need, that's what you get. So these GX12-whatever seem to be good for sensors and NEMA 23 motors. If you're going to run NEMA 34 motors, you may want to get GX16 connectors for those because they're a little bigger and let you handle a little bit larger gauge. I like these little ideal push to connect connectors for pigtailing all your high voltage stuff together. This wire is a little thick, a little harder to deal with, so that makes that job easy. The rest of this stuff all comes off eBay, and I'll let you look at that. Oh, I forgot this at the beginning. Have a coolant, have a relay in here for turning things like coolant off and on. So as I eventually someday I'm going to get a setup here where I can run coolant on one of my machines. I'll be ready, and you can see the little relay in there. So that's a 2-channel relay. I like to switch the hot and the neutral. I like to switch both of them. I suppose some people would only switch the hot, but I don't know, I feel like I'm a little safer if I switch both the hot and the neutral. So there you go. I hope that was helpful. If you're like me, the most difficult thing that you're going to encounter is finding a box to put all this stuff in. I like these ABS boxes. They're like a clamshell type of thing. I like them because they're relatively cheap, they're easy to work with, they don't conduct, so if you short something out, less likely to start a fire. But you can use a lot of different things. Just keep safety in mind. Try not to pick things that burn too easily. And finally, last but not least, be extremely safety minded when you're working with electricity. I don't usually put disclaimers at the beginning of my video, but I'm going to make sure there's one at the beginning of this video. Always be safe. If you don't feel like you know what you're doing with electrical things, maybe you shouldn't be doing it. And technically you probably should have all your stuff and inspect it by a qualified electromechanical technician before you put it into usage or let anyone come near it. So, all right, well, there you go. I hope that was helpful, and have fun building your CNC control box.